We utilize VQGAN for learning tactile representations and quantization layer absorbed into the decoder. After completing the autoencoder training, both the decoder and the discriminator are discarded and the encoder is connected to downstream tasks. We implement a training strategy that learns the representation just using a single simple object such as an Allen key or a small ball to simplify data collection significantly. However, the unit representation obtained through this training method exhibits robust transferability and generalizability. We conducted experiments on image reconstruction using the trained autoencoders across a series of unseen objects. Although trained only on a single simple object, UniT can effectively generalize to unseen objects. Compared to UniT, MAE performs worse. Moreover, the representation trained using an Allen key performs better than the one with the small ball. This result is logical as a small ball is one of the simplest objects. Despite this, the representation trained using a small ball can still capture features of unseen objects to a certain degree. We also show that UniT can effectively generalize across different sensors, even though the training data originated from a single sensor. Finally, we show marker tracking results, demonstrating that both UniT and MAE are capable of capturing dynamic marker motion information. This capability is crucial for applying these tactile representations to robot manipulation tasks with rich force interactions. We demonstrate the effectiveness of UniT on a USB plug 3D pose estimation task. We use OptiTrack motion capture system to label the ground truth 3D pose. In the data collection process, human move the USB plug randomly and we record the tactile raw images as well as 3D poses. For more details about the dataset, please refer to our paper and the open-sourced codebase. We benchmark UniT with training a ResNet from scratch as well as other representation learning frameworks, BYOL, MAE, and the state-of-the-art Tactile Representation Framework, T3. Based on experimental results, UniT performs best on this task. Next, we demonstrate the effectiveness of UniT in tactile-involved imitation learning. The first task is chicken leg hanging. The visual tactile policy with UniT handles this task effectively. This task involves rich force interactions with the objects being manipulated. The left arm applies force on the rack and stabilizes it, while the right arm exerts pressure to insert the chicken leg into the slot on the rack. Here are more rollouts with UniT. Training a visual tactile policy from scratch on this task tends to overfit on joint states, as seen when the right arm moves towards the rack without grasping the chicken leg. This issue likely stems from the high variance in tactile images due to the artificial chicken leg's texture. Adding tactile modality with tactile encoders trained from scratch may worsen the policy. For a visual-only policy, its ability to capture interaction information is compromised. As a result, the policy's performance is affected. Often, it appears that the chicken leg has been roughly inserted into the slot, but due to a lack of interaction information, the gripper is released too early, causing the chicken leg to ultimately fall out. The challenge of the chips grasping task lies in the fragility of the chips. The gripper must adjust accurately to accommodate the shape and size of the chips. Or it may lead to either missing the grasp or crushing the chips. Therefore, tactile feedback is crucial here. We can see that policy with UniT can handle this task effectively. This video showcases multiple rollouts using the visual tactile policy with UniT. Despite the continuous changes in the shapes and sizes of the chips, the policy consistently performs the task well. However, for a vision-only policy, relying solely on visual feedback makes it difficult to accurately determine the state of the grasp. This can easily lead to missing the grasp or breaking the chips when handling chips of different sizes. Finally, we demonstrate an Allen key insertion policy with UniT that achieves millimeter-level precision. During the insertion process, even if the initial attempt deviates from the nut, the policy can adjust based on tactile and vision observations, ultimately succeeding in inserting the Allen key. Here, we show multiple rollouts to demonstrate the effectiveness of the policy with UniT. Notably, we used 2 different sizes of purple racks for training data collection. Each rack size results in a different in-hand pose of the Allen key. The purple rack used for these rollouts is actually a different one and unseen in the training data. However, the policy with UniT can successfully generalize to unseen in-hand poses. For more comparison videos on this task, and more videos of other experiments, please refer to our project website.